All right, everybody, we've talked about what equilibrium means. It's basically that condition where the forward reaction and the backward reaction are going at the equal rate. So there's no net change in the concentrations. It's sort of the limit of the reaction. Once it gets to those concentrations of reactants and products, that's it. It doesn't go any further. Well, we'd like to have some way to express for every reaction, well, where is that point? What is the sort of ratio of products to reactants when the thing does come to a stop, when it does reach equilibrium? And the way we do that is this thing called equilibrium constant. It's a mathematical relationship, and nature's given us kind of a break. It's not too bad. But it's basically a measure of how far does the reaction go. So there's our sort of way we say it. KEQ is the number that we're going to measure. Well, as I mentioned, we're going to look at the ratio of products to reactants. So for this reaction right here, my big idea is K equilibrium, the equilibrium constant, equals some sort of ratio of SO3 to SO2 and O2. So it looks like this: SO3, SO2, and O2. Now, I want the concentrations of those. I'm going to use this bracket. That just means a concentration that's moles per liter. So how many moles per liter of SO3? And we can do the same thing for the reactants. And it's the product. So the mnemonic is sort of products over reactants. What's the ratio of the product concentrations to the reactant concentrations? Now there's one slight twist to this, and I want you, just before we go on, to notice that's like 2 to 1 to 2. For mathematical reasons that go way beyond this class, my equilibrium actually equals this: SO3 concentration, SO2 concentration times O2 concentration. And to make this math actually work, I'm going to put a 2 right there. Look at this. 2. Guess what I'm going to put here? 2. Oxygen, we don't have to write a 1. But all I'm doing is taking the coefficients from the balanced chemical equation, and they plug in right there. So that's it. We can do the math for any equation, for any reaction. If I know what it stops, you tell me the concentrations of the products, the concentration of the reactants, I can calculate this value of K, and it tells me how far it goes. Now, a few words about the units. Mostly good news, I think. Products and reactants. Products, reactants are always going to be moles per liter. There are other ways to do this, but for Chem 51, that's it. They're always going to be moles per liter. And the way we're going to remember, well, the symbol for that is these square brackets. Now, the good news on K is this. If you start thinking about moles per liter squared, moles per liter squared, moles per liter, the units on K could be a mess. But here's the best news we could possibly have. What would you prefer the units be? Equilibrium constant has no units. Again, there are reasons for that way beyond the scope of Chem 51, but no units. That makes our life easy. So I just have to remember that when I express the concentrations of the products or reactants, I use mole per liter, and when I get to KEQ, no units. So here's a few practice examples. There's my mnemonic. Products over reactants. Products over reactants. I look at A, KEQ equals O2 over O3. I go up to the equation and I see there's 3 of the O2s, there's 2 of the ozones, 2. That's it. What do we do? I don't want to make this video too long. And I understand everybody's not watching every video in its entirety, which is perfectly fine. It's like any other resource. You use what you need. So I don't want to make them overly long. They feel like they're about 22 hours each for me. Okay, let's look at C, for example. Silver ions react with ammonia to form this other funny looking ion. So my K equilibrium, I'm not going to keep writing KEQ, Ag NH3 2 plus over silver ion concentration times the ammonia concentration. And since there's 2 NH3s, I put a 2 there. And that's it. Products over reactants raised to the power of the coefficients in the chemical reaction, balanced chemical reaction equation. Now, let's actually do some math on page 7.22. And again, I know what the relationship is. I just plug and chug. So here's my reaction, very simple. Here's my equilibrium concentrations. Those are no longer changing. Once that thing hits its equilibrium, that's it. Now we know that the NO2 is being made and the N2O4 is being consumed, but they're also running in reverse. So KEQ part A equals NO2 concentration squared over N2O4 concentration. B says, well, what is the value? If you know the concentrations at equilibrium, 0.0325 squared over 0.147. And I get a number, 0.00719. And the units? No units. Now, here's a big idea. That equilibrium constant will not change. I could have different concentrations of the NO2 and the N2O4, and I'm still going to find at equilibrium that relationship, that ratio will stay the same. Now, I have to make one stipulation, one criteria, at same temperature. If I don't change the temperature, I can put any mixture I want. Eventually, the ratios, the forward and backward reactions will happen until it settles at that number. Then we can do math that's a little more interesting. We say, okay, if we know that's the equilibrium constant, and I know NO2 concentration, could I solve for the reactant concentration? Sure. Let's see. I'm going to say NO2 squared over N2O4 equals 0.00719. So let's see, I know this value, so I'm going to go 0.0250 squared divided by N2O4 concentration equals 0.00719. Now I'm going to do some algebra, and I get N2O4 concentration equals 0.0870. Now, I have to remember that the units we're using give me a concentration in moles per liter. That's it. For most cases, that's all we have to do. Now we have to think of maybe one other slight variation here, but that's it. That's the whole thing. What's the ratio of products over reactants? Oh yeah, raise their concentrations to the power, that's the coefficient, from the balanced chemical equation. Let's do this one. Now this problem is right in your book. So what I'd like you to do is you do this problem. You can find the answer in the book, but you set this problem up, 7.13. These problems that are early on in every chapter, the answer is right in the back of your book. If you don't have your book or whatever, you can text me or email me or something. I'll be happy to give you the answer, but I'd like you to stop and do that. Now, when I do this, let's see what number I got. I got 29. Here I just said look up the answer, and I'm giving you the answer. That's okay. You can work backwards from that. Try it until you get 29 with these numbers. Now, the question is, so what? Is 29 a big number? Does it go a lot? Is that a little? What does that really mean? Well, I'm going to say 29. Does it go very far? I don't want to get too technical, but yeah, sort of. It's bigger than, well. And does it make lots of product? Well, lots of product. Well, I would say not really lots. Well, then let's sort out K. Let's come up with some criteria for looking at K on page 7.24. Here's what we're going to do. We're going to say if K is a lot bigger than 1, say maybe bigger than 100, bigger than 1,000, we say that the ratio then of products to reactants is way more than 1. So the concentration of products is probably, well, it is more than the reactants. So we say, okay, if it's bigger than 1, products favor, the concentration of products is greater than that of the reactants. If it gets way up, bigger than 100, bigger than 1,000, then we can start to say, you know what, it's all products. But bigger than 1, technically speaking, we say, well, there are more products in concentration, higher concentration of products than reactants. So sometimes what we do is we say, well, this favors the products. If K is bigger than 1, we say it favors the products. If it's bigger than about 1,000, we say it not only favors the products, that's really all it makes. And sometimes we draw a symbol like this. We draw that and that, sort of showing like, well, it really goes a lot. Now we know there's some reverse reaction, but when this thing reaches equilibrium, it's really made a lot of products first. Well, the opposite case, what if reactants are much greater than products? I don't have a lot of products, but I still have a lot of reactants left over. Well, I can say it's much smaller than 1. The ratio of products over reactants is much smaller than 1. And so we say, well, it favors the reactants. Meaning whatever mixture you put in there, raw products and reactants, it'll settle down where at the end, the concentration of the reactants is much higher. And we draw that, we can symbolize it like this. Meaning at equilibrium, this thing has really shifted towards reactants and has not made much products. Well, what about this? If the reactant and product concentrations are about the same, we say, well, K is around 0. Around 0 means, well, around 0.1 to 10. I know that sounds funny to non-science folks, but somewhere in that kind of 1/10 to 10, we say, well, this is around a draw. And so we'd say, well, it doesn't really favor anything. We might say, well, around 1/10 to 10. That's when they're about equal. So now with this in mind, we can come down here and look at 7.12 and you go, that's a big number. That's much bigger than 1. In fact, that's bigger than 1,000. So we'd say, well, this favors products. That's much, much smaller than 1. This favors reactants. 24. Well, it's bigger than 1. It's not up around 100 or 1,000. So we wouldn't expect that we'd get 100% iron in CO2. But in the end, there's more iron CO2 concentration, well, than there are the reactants. So we say, well, technically speaking, this does favor the products, just not by a lot. All right, let's look at a twist on page 7.25. Here's my reaction. Looks a little messy. But if I said, okay, products over reactants, I would expect this. AgF squared times H2O times CO2 divided by Ag2CO3 times HF squared. I should have left a little more room there. I apologize for that. That's what we would expect. Now, this looks really funny, but the actual equilibrium constant expression is much simpler than this. It's actually only this. Divided by. That's it. Now, what do CO2 and HF have in common, or what do the others have that are not in common? And let me show you what I would actually plug in there. 1 squared times 1 times 1. On the bottom, I would have done that. And say, well, wait a minute, 1 squared, what do these have in common? Well, if I look at the Ag or the AgF, it's a solid. If I look at the let's look at this one. Ag2CO3 is a solid, and I plugged in 1s. Water's a liquid. I plugged in 1. The only things that showed up in my equilibrium expression were aqueous and gas. Now, there's a reason for that. Think about this. If I have a substance dissolved in water, can I change the concentration? Sure, you could put more stuff in water, or you could put more water in there. Yes, you can change the concentration. What about gas in a sealed container? Sure, you could inject more gas in there and increase the concentration. You could make the volume bigger, which would decrease the concentration. So the answer is yes. Substance dissolved in water, you can change the concentration. A gas, yes, you can change the concentration. Now, pure solid, if you add more solid, you don't change the moles per liter. If you remove some solid, you don't change the moles per liter. If you have a gallon of water, there's so many moles per liter. If you have a cup of water, you have so many moles per liter. These are really not variable. So what we can say is our equilibrium expression only applies to things that are aqueous and or gaseous. So we can sort of ignore solids and liquids. And even better, I think the trick for Chem 51 is, if I see the concentration of a pure solid, I plug in 1. If I see a pure liquid, I plug in 1. Mathematically, that works. Now, the implications of all this unchanging concentration of solids and liquids mean that pure solids and pure liquids have no effect, no impact on equilibrium. No effect. Is that the right word? Affect. Effect. And it's a little subtle, but it's because their concentrations can't change. So now that means my KEQ will be a function of aqueous and or gases only. I'm going to ignore the pure solids and pure liquids by plugging in a 1. Let's do one more problem. See how this works. Page 7.26. Right away I see solid right there. K equilibrium equals products over reactants, Pb2 plus times chloride raised to the second power over 1. So simply the iron 2 or lead 2 concentration times the chloride concentration squared. And I can go through and do the same thing. There's pure liquid, solid, solid. For each of those, I'm going to just plug in 1. So B is going to look really funny. B, KEQ equals 1 times CO2 divided by 1, which equals CO2. That's it. Now it looks kind of funny, and the reasons for this are a little bit complicated, but that's it. Let's do one more. C. K equilibrium equals 1 times carbon monoxide concentration divided by CO2 concentration times H2 concentration. I'll let you do D. And this is a problem right out of the book, but let's see. Let's do, oh, they're all about the same. I'm going to leave those. Those are in your book there. You can look them right up. If you can't find them or you don't have a book or something, let me know and I'll give you the answers. But it's the same exact thing. I'm going to plug in 1 for that. I'm going to plug in 1 for that. And I have no solids or liquids there, so that's going to be pretty straightforward. All right. That's sort of wraps up this equilibrium section in terms of doing calculations. The next section, we're going to say, okay, what if we have a section that's at equilibrium and we change it? We change the temperature or change the concentration by taking products or reactants out or putting products or reactants in. But this sort of wraps up what equilibrium is and what the calculations are. All right, I'll see you at the next video.